Good evening. Hello. Good evening, everyone. Good evening, everyone. Let's start today's session. I will first share my screen. Welcome to all of you for the sixth session of course MATLAB-based programming lab in chemical engineering. Myself, Prasil Kapadia. Just a short introduction. I have completed my BTech from SVNIT Surat in 2019. After that, I joined Reliance Industries Limited at Jamnagar and I worked there for a year. After that, I completed my master's from IIT Kharagpur in 2022. I learned this course from Professor Parag Deshpande, not the same course, not the exact course, but similar course. I learned from him there at IIT Kharagpur. Currently, I am pursuing my PhD from IIT Bombay. This is my web page, LinkedIn ID, and this is the YouTube channel where all the recorded videos are getting uploaded. In last week's session, what we basically learned how to solve a series of linear equations. To solve the series of linear equation, we learned first Gauss elimination method. Then we focused on lean solve command. Then we used inverse method. So let's just revise it once again because today's problem that we are going to solve is heat transfer through a cylinder, and that is this problem is solution of a linear equation. So let's just revise it what we learned in last week. So I will just write down one equation. Let's say 3a plus 4b is equal to 5, and a minus 4a minus b is equal to 10. Let's try to solve this coupled linear equation. So what I will do, I will first create a matrix of this left hand side with a and b coefficient. So first row is 3 comma 4 and second row is 1 comma minus 1. So this is my A matrix. My right hand side matrix is B matrix. My first row is 5 and second row is 10. Now to solve this, what I will do, I will write solution is equal to lean solve of A comma B, and I will run this. So when I will run this, I will get the solution. So see, I got the solution is minus 6.43 and minus 3.57. This is the kind of equation. This is the kind of equation that we have checked last. We have checked last week. After that, we took one more example of distillation column where benzene, toluene, xylene were getting separated, and for that it was told that feed flow rate is at some value, and due to some disturbances, feed flow rate is reducing in step of 5, and we were supposed to check how the flow rate of distillate and bottoms are getting affected. So this is the same problem that we also learned, and we solved that problem using lean solve command. So in today's class, we will be learning this problem statement, that is heat transfer through a cylinder. The theory behind this you have already learned in your heat transfer operation class. So let's take the example. I will read out the problem statement. Saturated steam at atmospheric pressure is owing inside a steel pipe of ID. ID means internal diameter 120 mm and outer diameter OD of 125 mm. So inside one steel, so assume that, wait, I will draw it. So here I am just drawing. Okay, we already have a figure. So see here, there is a steam. This is having steam, and pipe's internal diameter is 120 mm and outer diameter is 125 mm. Okay, now the pipe is insulated with 40 mm of insulation on the outer side. So after 125 mm, there is one, no, outer side insulation. Yeah, so here this is insulation of 40 mm. Why do we use insulation? Insulations are generally used when generally used to prevent heat loss, because it is industrially in industries it is not feasible that heat is getting lost when there are so many pipelines, and when fluid pass through pipelines, it should not cause heat loss. So that's why insulations are used. So here insulation thickness is given as 40 mm. So see here, there is steam here. uh, this is one steel pipe, and its outer layer is insulated. So here TS, here temperature of steam will be TS. That steel temperature will be T1. Here, after this wall temperature will be T2, and after this wall temperature will be T3. Okay. The convective heat transfer coefficients for inside the steam. Okay, where will convection happen? Convection will happen from steam here to here, and from here to ambient air. So the convective heat transfer coefficients for the inside steam and outside insulations are Hi watt per meter square Kelvin and H0 watt per meter square Kelvin respectively. The mean thermal conductivity of the metal is Ks. So we are just told metal's conductivity is Ks, that is steel. So they are writing Ks, and that of insulation is Ki. Ambient air temperature is 25 degrees Celsius. So this is the figure. As we discussed, steam is flowing here. Internal diameter, this temperature will be from steam here to here. There will be temperature T1, here to here T2. From insulation to outer layer of insulation, it will be T3. And ambient air, let's say it is T infinite. And here steam temperature, let's say is TS. Okay, so what we are told, rate of heat transfer from hot fluid to the wall. So hot fluid to the wall, it will be convection, and that is given by H into, what should it be? Convection HA delta T. So our H is H, A is 2 pi R L, and delta T is sum T1 minus T2. We'll figure out what will be the T1, T2, T3. Rate of the heat transfer from wall to wall. So that will be conductive heat transfer. So that is given by 2 pi KL T1 minus T2 divided by ln R1 by R2. There are three interfaces in this problem. Steam to steel. So here steam to steel, there is one interface. This will be convection. Then second is steel to insulation. Steel to insulation, this will be conduction. And insulation to ambient atmosphere. So insulation to ambient atmosphere, that will be again convection. By writing the energy balance at each interface, there will be three linear equations and three unknown temperatures T1, T2, T3. So these three equations, first we will be seeing how can we write this energy balance equation, and then let's see what we are asked to do. Analyze the variations in the interface temperatures, those are T1, T2, T3, as a function of Hi, H0, Ks, and Ki. We are given four values, Hi, H0, Ks, and Ki, and we are supposed to say what should be the optimum value, or can you come up with the values of above parameters which will minimize the outer layer, outer insulation temperature. Outer insulation temperature should be minimum. Okay, so before going to this complex part, let's first try to understand how can we write this material balance equation. So I will directly write those equations in MATLAB's comment section, so we can save our time. I will clear all, and I will do clear all and CLC. Okay. Here also I will do. I just want to clear this screen. So I will just do once again clear all and CLC. Okay. So let's write down the heat balance equation. So let's first write down the diameters we have. So in problem statement, okay, diameter of internal diameter of steel pipe is 120 mm and outer diameter is 125 mm. So let's say my D1 is equal to 120 mm. So I will write it down in meters because this H and HI, H0 are in watt per meter square Kelvin. So let's write it down in meter. 120 mm is 0.12 and its unit is meter. I'm writing unit in comment section. Now, outer diameter is 125 mm. So D2 will be equal to 0.125, 0.125, and its unit is meter. Okay. And D3. What is told for D3? 40 mm of insulation on outer side. So 40 mm insulation, how can we write it? So it is 125 mm plus 40 mm insulation. So it will be on both the sides, right? If we see it here, so 40 here, 40 here. So it will be plus 80. So that will be equal to 205, correct? 205 mm. So my D3 will be equal to 0.205 with units of meter. Okay. Now, okay. Steam temperature is not given to us, but let's assume that steam is water boils at 100 degrees Celsius. So let's take the temperature of steam at, or is it given? No, it's not given. Let's take temperature of steam Ts as equal to 373.15 because 100 degrees Celsius. So I will just add to 273.15 so that becomes 373.15 Kelvin. Okay, and ambient air temperature I am saying it as Ta. So it is already given 25 degree Celsius. So 25 degrees Celsius is 298.15 in the units of Kelvin. Okay, now we need HI, H naught, all values, but in problem statement we are told to vary these values. But for now, let's take first value HI. Let's take it as 1000. HI is equal to 1000 with units of watt per meter square Kelvin. This is my HI. My H naught is 1. Okay. So H naught is equal to 1. Okay. I should put semicolon everywhere else. What will happen? All these values will be printed and these we don't need. Okay. H naught is 1 and its unit is also same, watt per meter square Kelvin. Okay. So let's add this here. Okay. Now what is told? Ks and Ki, thermal conductivity. Ks Ks is equal to, let's take 10 first value and Ki is equal to 1. Ks is equal to 10 and its unit is watt per meter Kelvin. Okay. So this is Ks and Ki, thermal conductivity of insulation. So this is 1 watt per meter Kelvin. Okay, let's write down energy balance equation. So when I put double comments, what will happen? It will create one different section. See. So first I want to write down my equations for this first layer where it is going from steam to steel. Okay. So for steam to steel, my equation is what should be HA delta T. So H means H of, so see here, don't get confused. HI means internal and HO is of insulation. So just don't get confused here. So HI, H, A. What should be A? Area pi into D1 into L. HA into delta T. So delta T will be from steam to this temperature, Ts minus T1. Ts minus T1. And this should be equal to conduction. Correct? From T1 to T2. So what is conduction given by 2 pi K L, 2 pi K L into, from here to here it was convection. Now T1 to T2 is conduction. So T1 minus T2 divided by ln of R2 by R1. So here we are writing in terms of D2. So D2 by D1, it won't affect. So let's do one thing. Let's write first all equations, then let's understand what's happening. So see, section 2 I have created. So I will be writing my second equation. So second equation is from T1 to T2 conduction is equal to T2 to T3 conduction. So this equation from T1 to T2 is equal to, okay, I should put comment sign, equal to T2 to T3, correct? So it will be equal to 2 pi. Now T2 to T3 is insulation. So it should be Ki, correct? Ki into L into T2 minus T3 divided by ln D3 by D2, correct? Now our last equation, equation number 3, that will be equal to this conduction from 2 to 3 is equal to convection of 3 to ambient air. So this will be equal to, I'm just copying from here because I don't want to write it down again. We'll just edit it here. So it is H naught insulation of outer pi D3 into L, and temperature is T3 minus ambient air temperature. Okay. So let me just check my mic. Okay. So we have written three equations. Now, what is unknown to us? From all the equations, Hi we are assuming pi fixed value, D1 we know, L is cancelling out in all equations from both the sides. Actually, pi and L both are cancelling out from both the sides. So let's not worry about it. Ts we know, steam temperature we know, T1 we don't know. Right hand side T1 and T2. What is the unknown here from all these three equations? T1, T2, and T3 are unknown. So let's try to simplify this equation. So what can we write? Okay, I am cancelling out pi and L from both the sides. So my equation will be Hi into D1 into Ts, correct? First term minus Hi into D1 into T1 is equal to, let's write down first equation, 2 into Ks into T1 into divide by this term ln D2 by D1 minus same term but with T2, correct? T2. Okay, now what can I do? My equation earlier was, wait a minute, it's loading. My equation in earlier case was 3a plus 2b equal to 5. So what I did, let me write down two equations. 4a plus b is equal to 1. So see, on the one side, coefficient of a, coefficient of b, and on the right hand side, there were constant terms. So here also, can we do it? From this first equation, let me write down first coefficient of T1. So I am, okay, let's write it down, coefficient of T1. So minus this term, correct? And this term will come on this side, so it will also be minus, correct? This term. So for both this term, T1 is common. So this is my first equation that is multiplied with T1. Okay, first side. Now second is coefficient of T2 term. So this term will come on this side. So it will be plus this. Okay, so this is my coefficient of T2. Now, is there any T3 term? No, there is no T3 term. So let's write it down for now for sake of understanding. Plus, there is no coefficient. So I'm writing 0 into T3 is equal to right hand side constant terms. Okay, so what is the constant? This is only one constant term where we know everything, Hi, D1 and Ts. So this is our constant term. So in first equation, this T1 It should be minus sign here. So let's do one thing. Let's remove minus from here. Here it won't affect whether I write minus or plus. Here, let's add one minus, and from here, let's remove minus. Okay. So this is my first equation where I have coefficient of T1, T2, T3 and constant term. Similarly, what we will do, we will write down this equation also. We will have to break this equation. So 2 into Ks, 2 is also getting cancelled from both the sides, right? So let's just write down Ks into T1 divide by this term minus same but with T2, because yeah, so minus T2 is equal to same Ki into L into T2. L it is cancelling out. Ki into T2 divided by this term ln d3 by d2 minus same term but with T3. Correct? So here it is T3. Now what we can do, like earlier case we did, let's first combine terms with T1 coefficient. So this is the only one term where coefficient is T1. So I'm just writing it in better way of presenting. So it is understandable into T1. This is my first term. Now for my second term, my coefficient is T2. So this is the first, these two term. Correct? So this first term where coefficient is T2, and this term, it if I keep minus on outer side, so it will be plus this term. Okay, and its coefficient is T2. Correct? Now my coefficient of T3. T3 coefficient is there? Yes, T3 coefficient is there. So this is the term. So it will be plus of this term into T3. Into T3 is equal to right hand side. We have everything as 0. There is nothing constant term here. So our right hand side will be simply equal to 0. I don't know why it's not going here. Okay, it is automatically going down, but it is understandable, right? Yeah, it's solved. Okay, so in first equation, we have coefficient of T1 and T2. In second equation, we have all coefficients T1, T2, T3. Now let's write down the third equation. Okay, I'm sorry. Okay, let's write down the third equation. My third equation is this one. So let's break down this equation. Pi and L will be cancelled out. So 2 into AI into T2 divided by this term. So it is the coefficient. Okay, let's first write down all equations. Minus same equation but with coefficient of T3. T3 is equal to this whole term into T3. Okay, where L is cancelled out and pi is cancelled out, and the same term minus T minus this T. Okay, now let's combine. So first equation, there is no coefficient of T1, so I will write down 0 into T1. Now for second term, coefficient of T2 plus, this is the only equation where there is T2. So this term into T2. Now T3 term. So minus this term minus, I'm keeping minus outer side. So this term and this term will be plus h naught into d3, and this whole term is multiplied with t3. Now this is equal to, do we have any constant term? Yes, we have this term minus h naught d3 ta. Okay, so it is minus h naught into d3 into ta. So we have three equations, t1, t2, t3, and three unknown. We can cross check our equations from here. 2k divided by ln d2 by d1 plus hr into d1. Yeah, we are getting exactly same equations. So this is how we can get this equation. Guys, just give me a minute. There is someone here. Hello. Yes. So see, there are, I don't know what I'm getting. Okay. So here we have camera is on, mic is on. Yes. So see, here we have three equations and three unknowns. Now we want to solve these equations. So let's write it down. Okay. So here, okay, we will have to write down three coefficients. First matrix, let's say it is A1. Okay, let's first write it down for T1, where temperature T1 is coefficient. So our matrix will be A1 is equal to this term. This term is my first. In first equation, this is the coefficient of T1. In second equation, the coefficient of T2 is this one. Coefficient of T1 is this one. Correct? And in last equation, there is no T1 term. So A3 is equal to null matrix. So I'm just writing it as 0. Now let's write down T2. And I'm calling it as B1. B1 is equal to, okay, minus this term. Correct? So this is my B1, my B2. In second equation, coefficient of T2, this huge term. Okay. And in third equation, B3 is equal to, in B3 or in third equation, my coefficient of T2 is this one. Okay. Okay, so this is done. Now I will be writing coefficient of T3. So let's say C1 is equal to, in first equation, there is no coefficient of T3, so it is 0. My second equation, coefficient of T3 is this term. Okay, so this term in my third equation, coefficient of T3, it will be huge term, correct? Okay. So we have three equations. Now I will be writing right hand side RHS. So let's say D1. So what is RHS in D1? So it is this value. Okay. So this D2, it was I think null. There was nothing in D2 and D3 where this term minus H naught into this thing. Okay. So one thing before proceeding ahead in MATLAB, there is not ln, it is log. We can't write ln, we have to write log. Well, let's see, when I write log. So when I write log, it takes natural logarithm. So see here natural logarithm, but when I write log 10, it takes base 10. So here we have no natural logarithm. So from all, we have to remove ln. We have to replace ln with log. Log. Okay. So now what we need to do? Okay, so this is done. Now what we need to do? We need to find a solution. So let's prepare two matrix A and B. My first matrix A is equal to coefficient of first equation. So it will be A1, B1, C1, correct? A1, B1, C1. So coefficient of T1, T2 and T3 in first equation, correct? Now let's write it down for second equation. A2, B2, C2. And similarly for third equation, it is A3, B3, C3. Yes, this A3, B3, C3, this is my A matrix. Now for B matrix, my coefficient is D1, first row, and for second row, it is D2, and for third row, it is D3. Okay. Now what I need to do, T is equal to lean solve of A comma B. Let's try to solve it and see what are we getting. There is no, okay, here I have written H0, not, okay, here it is H small o. And when I am writing this equation here, I am writing H0. So it should be H small. Let's check it here. Yeah, it's correct. Now let's rerun it. Yeah, this we don't know actually. We don't need, I'm rerunning it. So see, I have T1, T2 and T3. T1 is highest 373. T2 is 373. Similar T3 is 369. Not a huge gap. But now what I need to do, I have to vary my HI values, correct? So we will have to add one loop. So let's add loop here. So I will write as 4. We will have total 4 loops, right? Because we have to vary 4 values of HI, sorry, here, HI, H naught, KS, KI. So I will write down 4 loop. 4 HI is equal to what value? 1000 to 2500. Let's say we are going in interval of 100. Then 4 H naught is equal to, it is given from 1 to 10. So let's say 1 to 10 in interval of 1. 4 K S 10 to 100 is told. So let's say from 10 to 100 in interval of 5. And 4 Ki is equal to 1 to 10. Let's say here I am going with interval of 0. But let's say here also going 1 and here also let's go in interval of 10. So we need to close first all these loop. Okay. So here it's not the way we want to write. So I will just use one smart indent. So it will fix it will just improve the view. So where is this smart indent? See here it's okay. So we have four equations. Now what is told to us? Let's try to understand what is told to us. Can you come up with the values of above temperatures which will minimize the outer insulation temperature? So from these also it is visible that T3 is minimum from all these three. So what we'll do? Okay, let's first differentiate this. T1 is equal to this T of 1 is my T1. Then T2 is equal to T of 2. T3 is equal to T of 3. And T4. No, there is no T4, correct? Correct. Now, okay. So what should we understand from here? There should be no heat loss, right? Between T2 and T3. From T2 and T3, there should be no heat loss because we are keeping one insulation. So what we can assume that let's put one condition that if absolute value of T2 minus T3, correct? Let's say it is less than equal to 1. Then only I will print my output that is equal to okay. So here I want to okay. Let's do one thing. Let's first run the code and see what we are getting. So when I run this code, it's going to take time. So see, we are having here every values is not getting printed. It's only printing the final values. It's not printing everything, correct? But I want everything at once. So what I will do, I want to save my output. So what I will do here, I will create one null matrix. Wait, it's not working. So here, yeah, here, laptop is getting slow. Just a minute. Here, I will create one null matrix with name output. So output is equal to my null matrix, correct? Just a minute. Yeah, it is hanging because of this thing. I need to just a minute. It's okay. Okay. So now what I will do after every value, I will print my output. So output is equal to output previous. Okay. Let's see. First, I will write T1, then T2, then T3, then HI, H0, KS, KI. Okay. Now, what will happen after each loop? I want to print it. So what I will do, I will first write output and I will put one semicolon. So after first loop, this value will be saved. Then for the next loop, it will go in the next column because of this semicolon. So now let's run and see what we are getting. So see here we have output. There are total 16,000 outputs. Now what we want, insulation should be such that my this difference T2 and T3 should be minimum. Okay, so let's write one if loop. So if let's say absolute value of T2 minus T3 is less than equal to let's say 10. Okay, then only we will print. Okay, then we'll print, else we will continue. Okay, let's use smart indent here. Okay, now let's run it and see how many points we are getting where T2 and T3. Okay, there is one for and loop missing. Yeah, after if we need to put one and that we have not added. Now it's fine. Okay, now let's run it. So see, our output is still huge values 14,080. So 10 is still huge value. So let's go to 10 to 5. Number has reduced, but it is still a huge number. Let's go for 1. And difference is 1 less than equal to 1. Still there are 1600 solutions. Let's go and let's think. Let's say I'm going for zero point 0.5. 0. Let's go for 0. So exact 0, there is no solution. Let's say zero point 0.1. So zero point 0.1 also no solution. 0.2 no solution. 0.3 0.3 no solution. 0.4. So for 0.4 there are 160 solutions. Let's say 0.39. Same 160 solutions. 0.38. 160. 0.37. Okay, so my all values are getting less than 0.38. So I have 160 solutions. Now from this 160 solution, I can choose some optimal solution that is economically feasible, as well as always it is feasible. So here what we can now further do, but it will increase our timing to run. So here we have given huge difference. So let's go in interval of 10 here. Here 0.1. Here let's go in interval of 5, and here also 0.1. It will take time, but let's see how many solutions we are getting now. I guess we'll get more amount of solution because we have increased our search space. It will take time to run. It's still taking time. Let it run. Because we have huge matrix. So see, still here we are getting 2,869 solutions. So now we won't see much by this difference, but you understand how we can solve this kind of problem. So this was all for linear equations. Now, so I'm stopping this linear equations part, solution of simultaneous linear equations for now, because there is nothing much here. So in linear equations part, we learned lean-solve command, how to solve it using lean-solve MATLAB inbuilt command. Then we learned inverse matrix method when we write A inverse into B. Then further we learned Gauss elimination method to solve these linear equations. Now let's move ahead from linear equations to ordinary differential equations. Okay, so for that, I will. Yes, so for this, I will open OneNote, and for some time, for amount of some time, I will stop my camera so I can easily write down what I want to write. Okay. I guess my screen is visible. Let me check my mic is on and screen is being set. Okay. So now, okay. So now we will see differential equation. So differential, just a minute. Differential equation. So what is differential equation? There are two types of differential equation: ordinary differential equation and partial differential equation. So differentiation with respect to single variable. So let's say dy by dx is equal to minus x by y. So differentiation is only with respect to x. So this is called ordinary differential equation. Let's say I'm writing dy by dx is equal to x square plus y square. So here also differentiation is with respect to one variable only. So this is also called ordinary differential equation. Further, one more example, d square y by dx square plus y is equal to 0. So here also differentiation is with respect to one variable. So this is called ordinary differential equation. Now what is degree of, what is first order of order of differential equation? So order is called, the order of differential equation is the order of highest order derivative in the term. So here highest order derivative is 1 only. So this is order 1. Here also same 1 and here order 2. Order is 2. Now what is degree? Degree is power of the highest order derivative. So here dy by dx power is 1. So here power is degree is 1. Here also in all cases degree is 1. Okay. Let's take this example. D square y by dx square whole square plus c into dy by dx plus ky is equal to 0. So here order is 2, and for this highest power, uh, highest order, that power is 2. So here order and degree both are is equal to 2. So these are called ordinary differential equation. What is called partial differential equation? Any equation involving partial derivation of one or more functions with respect to one or more of the independent variables. So let's say I'm writing del y del t is equal to k del y del x square. So here derivative is with respect to x and t. So it is called partial differential equation. Your heat conduction equations. Del t by del t is equal to minus ka del square u by del x square plus, sorry, del square t by del x square, del square t by del y square plus del square t by del z square. So here temperature is varying with both temperature and coordinates x, y, z. So this is called partial differential equation. Now we will only focus as of now on ordinary differential equation. So how to solve these equations numerically? So we'll start with Euler's method. So first is Euler's method. Okay. So Euler's method. How can we derive Euler's method? So it is from what is this called? Central function. Central mean value theorem. So mean value theorem says that if a function is continuous and differentiable between 2 points x1 y1 and x2 y2 on the function, then the slope of the line joining these 2 points is equal to derivative of the function at one another point, let's say c. So derivative at point c is equal to y of x2 minus y of x1 divided by x2 minus x1. Okay. x1. So what I will write here, let's say C is x1 and h is x2 minus x1. So I can write y of x2 minus y of x1 is equal to h into y prime of x1, and this y prime of x1 I am telling it as f of x1 comma y1. y of x2 minus y of x1 is this. So y of x2 is equal to h into, sorry, y of x2 is equal to y of x1 plus h into f of x1 comma y1. For simplification I can write y2 is equal to y1 plus h into f of x1 comma y1. This is nothing but my equation for Euler's method. I hope this is clear to everyone. My video won't be visible right now because I am writing it in OneNote. So this is what Euler's method is. Now if we go for further complex method, so one method is Taylor series. Taylor series we have already learned. It is given by y of x1 plus h, or y of x2 is equal to y of x1 plus h into h into y prime of x1 plus h square by 2 factorial into y double prime of x1 up to so on. So if we reduce these terms, h we take very small, then it will reduce to this term only, and this is nothing but Euler's method. So for that we need to take very small value of h. Now another method is RK method. So RK methods are of two type, order 2 and order 4 method. So in order 2 method, we write same way, y2 is equal to y1 plus h into, here we don't write f, we write s, and we define s is equal to s1 plus s2 by 2, and s1 is my function at x1 comma y1, and s2 is my function at x1 plus h, next point x2 plus h, and x1 plus h and y1 plus h. So x2, no, sorry, h1 plus x1 plus h and y1 plus s1 into h. At this point, we are finding derivative. So this is similar to Euler method, only we are not directly taking this function. We are manipulating function and then we are adding it in terms of s. Now RK4, order 4 method, how do we write it? So it is same, y2 is equal to y1 plus h into s. But here s is equal to 1 by 6 s1 plus 2s2 plus 2s3 plus s4, and here my s1 is same, f of x1 comma y1, my s2 is f of, now here it was x1 plus h, so I am taking now x1 plus h by 2, here y1 plus s1h, so y1 plus h by 2 into s1. My s3 is equal to f of x1 plus h by 2, this term is same, y1 plus h by 2 into, now here it is s2, and my s4 is equal to nothing but simple f of x1 plus h, y1 plus s3 into h. So this is how we can solve our ordinary differential equation numerically. Now let's try to convert this whole exercise in terms of, so give a minute left. laptop to settle down. Yeah. Okay. Okay, so this is not yet. How do I open Teams now? Wait. Okay. So now here, right now I'm at Teams. I will have to open my MATLAB. I don't know why it's not getting. Just a minute. I'm not able to. I'm not able to start anything. Just give me a minute. Uh, I will search for MATLAB here. And I will open again my presentation from here. It's not restoring it in its initial size. That is the issue. Okay, let's start our walk because this is not working in this way. So I will. Yeah, see MATLAB is here. Okay. Okay, I don't know why it's not working out. But let's start. Let's write down the code for this these methods. So let's first start with Euler method. Let's see the example problem that I'm taking is it's not setting it again. So I will first write down clear all and CLC. Then I will add. Let's say I want to solve this particular equation dy by dx is equal to xy. This differential equation I want to solve, and I'm given that y of 1 is equal to 5. What does this mean? When I'm putting x is equal to 1, I'm getting y is equal to 5. This is my solution. So let's say I want to solve my equation from 1 to x is equal to 1 to 1.5. Okay. So let's first write down the x values. X values are from 1 to 1.5. Let's say I'm going in interval of 0.1. Okay, let's say I'm going from 0.1 to 1, 0.1 to 1.5. So here my h will be equal to 0.1. But let's say I'm not counting h. I'm not directly writing h. I'm counting h. That is equal to x of 2 minus x of 1. This will be my h. Correct? And my y of 1 is equal to my first value of y is equal to 5 corresponding to first value of x. Okay. Now let's write down a code for Euler method. Euler method. Euler method. So what my equation is y2 is equal to y1 plus h into s. So y2, so y of I plus 1 is equal to y of I plus h into my equation. Equation is my x into y. So it is h into x of I into y of I. This is my equation. So I will run my loop for I is equal to 1 to last value of x. So that is length of x. I will run this. So I should get my solution. And I will say my solution y is equal to, I'm seeing this y as y of Euler. And let's try to run this. So see, I have received the solution as this points 5, 5.5, 6.1050, 6.8376, 7.7265, 8.80, 10.12. This is using Euler method. Now, let's write down the same thing. Just a minute. This is not. I will just stop sharing my screen. Give me a minute. Yeah. Okay. So I will rewrite that part. we wrote our equation is dy by dx is equal to xy, and we are told that y of 1 is equal to 5 and interval is 1 to 1.5. Correct? Now, my screen is visible now. Now, okay, so let's solve this first using Euler's method. I'm re-showing it 1 to 0.1 to 1.5. This is my y. X, my h will be second value of x minus first value of x, and my y of 1 is equal to 5. Correct? Now, let's first solve it using Euler method. So Euler method says that y of I plus 1 is equal to y of I plus h into f of x. So x of I into y of I. Okay. So for I is equal to 1 to length. For I is equal to 1 to length of x. This is the equation, and I will put one and here, and I will say my y Euler is equal to y. So this is my solution. So let's run this code. Let's run this code. LENGTH. Okay, spelling mistake. So when we run this, we have Euler's method. Solution is y. So see, these are the solutions. This is 0. This is 1, 1.1, 1.2, 1.3, 1.4, 1.5, and 1.6. It won't stop at 1.5 because it is already when I am going for length of x. So last value of x is 1.5. So it will calculate at I plus 1. That is 1.6. That's why we are getting 6 points. Now let's try to write down the same thing using RK2 method. Okay. So for RK2 method, I have first S1 is equal to correct. This is my S1 and my S2 is equal to xi plus h into phi of I plus S1 of I into h. Okay. So this is my S2 term. Now my S is equal to this S1 plus S2 whole term divided by 2. This is my S. And I write y I plus 1 same, this same term but only difference is it is h into s of I. Okay, so this is how we calculate using RK2 method for I is equal to 1 to LE length of x. And I will put one end here, and we will use smart indent for better representation. Smart indent. And I will write this y as RK2. So let's see what is the difference in RK2 values and Euler method. So see, there is slight difference in RK2 method and Euler method. We can see 5.5, 5.5, and here it is 5.5525, 6.2 and 6.1. So there are slight differences between Euler's method and RK2 method. Let me write down the same thing for RK4 method. So for RK4 method also, it is the same thing, correct? But only we have four terms, S1, S2, S3 and S4. My S1 is same. Here for my S2, it is H by 2 and S1, S1 by 2. S1 into H by 2, correct? Now my second term, third term, S3 of I is equal to same. Here it is S2 of I. And my fourth term is nothing but this term. But here instead of S1, in RK4 method, it is S4, S3. Okay. And this equation we'll have to modify 2 into S2 plus 2 into S3 plus S4 I. This whole term is divided by 6. And now let's see what we are getting. Okay, I need to write here RK4. I'm sorry. So see RK4 method, Euler method 5.5, 5.5525, 5.5536. But we don't know what is the actual solution. So actual solution of this dy by dx is equal to xy. Y actual is given by phi into exponent of minus 1 by 2 into exponent of x square divided by 2. This is my actual solution. When you solve it equation analytically, this is the solution that you get. Okay, so let's see what I am getting from y actual. So see, my y actual first value is 5.5536. That is exactly matching with 5.5536 when we are using RK4 method. So this says that solution from RK4 method is better with same value of h. Correct? Okay. So now what we need to do? Now let's plot our solutions and see what we are getting. So I'm plotting it. So how can I plot it? Plot of x is fixed, x comma y underscore. First let's plot Euler. Then I will keep hold on. I will plot x underscore x comma y underscore RK2. I will again keep it on hold. Then I will again plot x comma y underscore RK4. I will again keep one hold on command. I will again plot x comma y underscore actual and I will just plot it. So let's use legend. First one is Euler. Second one is RK2. Third one is RK4. And fourth one is actual. So let's plot all this and see what we are getting. Okay, there is some issue with coordinates. Okay, so what we can do here, it is y is getting one more value. So let's do length of x minus 1. So it won't take last value. Okay, now we won't face this issue. It is still running. And okay, the plot is here. I will open it in new tab. So see, this is Euler method. RK2 is still seeing as red one, but RK4 and these actual are exactly coinciding with each other. So what we can say that for the same value of h, listen my statement really carefully. For the same value of h, when my value of h is constant for all the cases, RK4 will give me accurate results. Okay. Let's say I'm reducing my value of h from 0.1 to 0.01. For case of Euler's method, it will automatically apply for every method. But let's see what we are getting with Euler's method. Now, if we see the plot, so see, when we check the plot now, we can see that Euler method is doing well, but not exactly matching, but the solution has improved. Now let's say I am further reducing this 0.01 to 0.001. It is going to be computationally expensive because it is calculating value of y at more number of points. Okay, so from 51 to it is going for 501. So see, for extremely small value of h, you can see that see it is exactly matching with actual solution. So what is the benefit? The benefit is our solution has improved, but what is the disadvantage? The disadvantage is that our solution, our computational efficiency has reduced because you saw that the time required to complete that calculation has increased when we are reducing the value of h. So what can we conclude from here? RK4 method is excellent even for small values of h. And if we want to use our Euler method or RK2 method, we need to really go for less values of h, and this can increase our computational load. So this is what we learned. So we will what we learned how to solve differential equations numerically. For that we checked this Euler method, RK2 method and RK4 method. Okay, and we check the actual solution and we try to match which method is best. There is one more thing that is ODE45, but we will not learn it today. We will keep it for next class. Okay, so let's take small problems. Okay, let's take small problems. So we will go for multiple choice questions. These may help you in solving your assignments. So these two problems, first problem is series reactions using continuous stirred tank reactor and CSTR in series. These two problems we will take in the next week's lecture, where we will learn how we can solve these coupled differential equations using ODE45. Or in today's this problem only, these MCQ questions only, we will see how we can solve using ODE45. Okay, so this is the first question. The simplest approach to approximate first derivative of a function f of x is using the definition of a derivative as f prime of x is equal to limit h tends to 0 f of x plus h minus f of x divided by h. Consider f of x whose tabulated values are given. What is the value of h in this case? So for x is equal to 1, f of x is 1. For x is equal to 2, f of x is 4. 4x is equal to 3, f of x is 6, x is equal to 4, f of x is 8. And what is h? H is x2 minus x1. So for this case, we can see that x2 is 2, x1 is 1. So 2 minus 1 is 1. So my value of h is 1. Okay. So what kind of function it will be? For x is equal to 1, it is 1. X is equal to 2, it is 4, 3, 6, 4, 8. Okay. Let it be. Okay. So my value of h will be equal to 1. Okay, let me write it down here. My h is equal to x2 minus x1. That is 2 minus 1 is equal to 1. So my h will be equal to 1. Let's move it with the next problem. Compute the derivative of f of x is equal to x cube minus 6x square plus 11x minus 6, 4. Range of x is given 0.01 to 0.04. Using MATLAB inbuilt function diff. This we will see. Consider the step size as 0.01. So we are going to move from 0.01, 02, 0.03 and 0.04, and we are supposed to find derivative between these two values. So we will use diff inbuilt MATLAB function. Okay, so let's check. So let's first check what is diff. So I'm writing diff. Okay, and let it show what is what really diff does. Diff is difference. So see, when I write difference of x, so 1, 1, 2, 3. So 1 minus 1 is 0, 2 minus 1 is 1, 3 minus 2 is 1. So I am supposed to find difference between 0.03 and 0.04. So what I have to do, I have to find first the derivative. Correct? So my value of x is, from question, it is x is equal to 0.01 to 0.04 in interval of 0.01. And my h is equal to 0.01. Now my function f is equal to, what is function told to us in problem statement? X cube minus 6x square plus 11x minus 6. So it is x cube. I will put dot because it is scalar operation. X cube minus 6 into x square, sorry, here, plus 11x, 11 into x, oh, sorry, here, minus 6. Okay, so derivative will be given as difference between f. Correct? Difference of f divided by h. So we'll get derivative. Let's see what we are getting. 10.8207, 10.7019, and 10.5837. And we are told, we are asked to tell the derivative between x is equal to 0.03 and 0.04. So our answer will be 10.5837. Okay. Okay. Moving ahead with the next problem. Compute the integral of x square plus 3 dx using the trapezy inbuilt function in MATLAB. Give your answer rounded to the nearest integer. Consider x is equal to 0, 0.5, 1, 1.5, and 2. This code, how we can write our own code to find integration using trapezoidal rule. This we will see in next class. But let's try to solve this problem using trapezy function today. Okay, so let's search how it works. TrapZ. So TrapZ computes the approximate integral of y via trapezoidal method. So trapezoidal method, this is trapezoidal method. So see, this is actual solution, exact function, and these are the values obtained using trapezoidal rule. So there will be slight inaccuracy. So this is the trapezoidal rule b minus a divided by 2 f of x1 plus 2 into f of x2, all points multiplied by 2 and last point with no multiplication. Correct? So we are supposed to solve this problem using trapezoidal rule. So first we need to define our x. So x is given as 0, 0.5, 1, 1.5 and 2. This is the range of x I have 2. And my y is given as x square plus 3. So y is equal to x square plus 3. This is my y, correct? So integral is given as the syntax of trapezoidal rule. Let's check it again from here. It is x comma y. X comma y. Okay, let's see what is the value of integration that we are getting. We are getting the value of integration is at 8.75. Okay, let's see what is the actual value of integration. My actual value is x square plus 3. So x square's integration is x cube divided by 3 and integration of 3x. And we are going to find from 0 to 2. So 0 to 2. So it will get 2 cube 8 by 3 plus 6. So what is the value of 8 by 3 plus 6? Let's check it here. Plus 6. So actual answer is 8.6667 and what we are getting from trapezoidal rule is 8.75. So what we can do to get our exit point, so we can reduce these points. So instead of going in interval of 0.5, let's go in interval of 0.1 and see what we are getting. So see, we are getting very close answer, 8.6667 actual value and 8.67 our trapezoidal rule. If we further reduce these points, so see we are getting exact answer 8.6667. So this is how you can improve in accuracy of your numerical methods by reducing your step size, but simultaneously what is going to happen, this is going to increase your computational load. Correct? So let's move ahead. Okay. So let's move ahead to the next problem. Question 4. Identify the correct statements. The order of an ordinary differential equation is the order of the highest derivative in the equation. This we checked, right? This statement is correct. Order of the highest derivative is called order of the ordinary differential equation. So this statement is correct. This statement is correct. Now next statement, the degree of an ordinary differential equation is degree of the derivative of the highest order in the equation. This statement is also correct. We learned what is the degree and what is the order of ODE. Third statement, the degree of ODE is the highest power appearing in the equation. This is completely false. So what is the correct answer? Both statement 1 and 2 are correct. Okay. Now let's move ahead with the next question. That says that an ODE is termed as stiff if two or more dissimilar scales in the independent variable are involved. For a set of ODEs, the stiffness is quantified in terms of stiffness ratio. The stiffness ratio is defined as the ratio of real parts of the maximum and minimum eigenvalues of the Jacobian matrix. Jacobian matrix we have already learned in last to last class. So those who don't know Jacobian, please follow that lecture. Consider the following system of ODEs. dy by1 by dx is equal to minus 1.2 y1 plus 1.5 y2. In my second equation, dy 2 by dx is equal to 40 y1 minus 190.3 into y2. Determine the stiffness ratio for the system using Jacobian and eigen inbuilt functions. Okay. So see, stiffness ratio is defined as the ratio of real parts of maximum and minimum eigenvalues of the Jacobian matrix. So first what we need to do, we need to find the Jacobian matrix, and after Jacobian matrix, we need to find the eigenvalues of the Jacobian matrix. And after finding eigenvalue, what we'll do, we will find the ratio of maximum eigenvalue divided by minimum eigenvalue. Correct? So let's try to solve this equation. So this is symbolic. We will use symbolic tool. So I will use y1. We have two y1 and y2. Correct? We have y1 and y2. So my first equation f1 is equal to minus 1.2 into y1 plus 1.5. Sorry, 1.5 into y2. So this is my first equation. My second equation f2 is equal to 40 y1 minus 190.3 y2 into y1 minus 190.3 into y2. So I have written down two equations f1 and f2. Now I will write it down. F is equal to f1, my first equation, semicolon f2. Now what I need to do first, I need to find the Jacobian of my f, and with respect to my two variables y1 and y2. So I will write, let's say m is equal to Jacobian of which matrix? F matrix, and Jacobian with respect to y1 and y2. So what I am having right now, I am having Jacobian matrix. Okay, let's try to run till here and see what we are getting. To see, my Jacobian matrix is this one. Okay, now I need to find the eigenvalues of this matrix. Okay, so E is equal to eigenvalues are estimated by using EIG inbuilt function. So EIG of M. Correct. So let's see what we are getting as eigenvalues. So see, these are my two eigenvalues. Really a weird number. I'm sorry, just a minute. Okay, now what I need to do, I need to find a ratio of maximum to minimum eigenvalue. So I will write down as stiffness ratio is equal to maximum of EIG. Let's read it down again. Real parts of maximum and minimum eigenvalues. So maximum divided by minimum. Okay. So let's see. Okay, no. It should be E. Okay, but we are getting this weird number, but I don't want it in these terms. So what I will do, I will double this. Double is a format. I'm not doubling it actually, but double is a format. So let me stop it here and see what is the value of E that I'm getting. So see, it is minus 190.6168 and minus 0.8832. So now it will give me in correct answer. So my stiffness ratio is 0. Okay, one more thing. We need to take absolute, not this actual value. We need to take absolute value because it's a ratio. We need to take absolute of both. Now let's see. So my stiffness ratio is coming out to be 215.8158. Okay. So this is how we can calculate stiffness ratio. Okay, now let's move ahead with the next question. The initial condition is y of 0 is equal to 0.01. Integrate up to x is equal to 0.8 and report the value of y of 0.8. Truncate the answer to the two decimal places. And my equation is dy by dx plus xy divided by 1 minus x square is equal to x into square root of y. So let's learn here. Let's try to solve this problem using ODE23 function. So let's see what is the format of ODE23. So see, this is my syntax of ODE23. So I need to write t comma y. Y is my solution is equal to ODE23. ODE function, that is my equation. T span, time span, that is given to us. And T span is 0.8. So 0 to 0.8 and y0 is given to us as 0.01. Okay. So this is how we can write it down. So let's write it down our own system. So let's say y0 is equal to 0.01. It is given in the question. Then x span is equal to 0, 0.8. Correct? And my solution is given as t sol, y solution is equal to ODE23. What is the syntax? ODE23 at the rate my function t span and y0. So at the rate I will call ODE. So I will write down that function at the rate ODE1. Let it say ODE1. My x span comma y0. Okay. So what we can do, I don't want to write it down in terms of function. So what I will do here, I will write it down as f is equal to at the rate of x comma y, and my equation is divided by x into square root of y. Just give me a minute. Yes, my equation is x into square root of y. So I will write it down x into sqrt of y, x into square root of y minus x into y divided by 1 minus x square. Okay, here I will suggest to put dots because we are dealing with. So now let's check what we are getting. Oh, yeah, here it is f, not OD1. Uh, yeah, see, f, x span, t span. So see my answer. And what I am asked in question, it is asked that truncate the integrate up to x is equal to 0.8 and report y of 0.8. So I just need my last solution. So what I'll do, I will write that y of end. I just want to print y of n. So answer that is told to us, or that is what we are getting, is 7. No, answer is not 7. Not y of n, y sol of n. Okay. 0.0465. This solution we need to print. So that is coming out as 0.0465. So this is a really simple way. Let's say if I am solving this equation using ODE23. So what I will write, okay, let me do it in new space. So I will write down these things will be remaining same. Correct? My function f is equal to at the rate of x comma y, and my equation is x into y. And I will just write my solution t sol comma y sol, or x, we are using x here, so let's call it x sol y sol, is equal to ODE23, my function f, my value of x, and my value of y of 1. Okay, if we solve this, so see solution that we get. And similarly ODE40, sorry, what was the name, which uses RK4 method. So that ODE is called ODE45. So when we use ODE45, so we'll have better accuracy. Okay, so this is how we can solve. Okay, let's solve the same problem using ODE45. Let's see what we are saying. Our answer that we are seeing right now is 0.0465. Okay, it's not changing with ODE45 too. Okay, okay, now let's move ahead with the next problem. So this is how we can solve our equation using MATLAB inbuilt ODE functions. Correct. Now let's move ahead. Let us consider a first order reaction in a batch reactor, for which the rate equation is given by dC by dt is equal to minus k into c. The reaction rate constant K is 5 to 10 raised to 2 R inverse. So 500 R's in R inverse. At T is equal to 0, C is equal to 1. Which solver takes more time to compute the variation of concentrations of the reactant with time up to T is equal to 0.0002 hours, ODE45 or ODE23. So here we are supposed to say that which solver is more time consuming, ODE45 or it is ODE23. So let's write it down. Okay, let's write down our equation. First, let's do clear all CLC. Okay, we are told that C0 is equal to 1 and my T span is equal to 0, 0.002. Correct? 0.00 triple 02, not 00, 0002. Okay. So now I will write down my equation, right? T sol comma y sol is equal to ODE45. Okay, here I need to write down my function. So I will write f is equal to, what is my function? My function is minus k into c. So minus 500 into c. So my function is equal to at the rate of t comma c, it is minus 500 into c. Correct? So ODE45, what do we write here? F comma t span comma C0. So this is my solution using ODE45. So I'm telling it here as 1 and the same solution 2, but that using ODE23. Correct? But here our task is not to find a solution, but our task is to find which solver is faster or which solver is slower. So for that, there is MATLAB inbuilt command. So I will start with TIC. I will just write TIC. So this will start our stopwatch, and time underscore ODE45 will be equal to TOC. OC means it will stop. Same thing we'll do TIC. The solutions we don't need right now. We need time. And same thing we will do for ODE23. And let's see what we are getting. So see, ODE45 is taking longer time than compared to ODE23. Let's see if I'm reducing this from, it is obviously going to more for ODE45 in all cases. So this is how minus k into c, my value of, what is the value of k? 5 into 10 square. Yeah, it is correct. Yeah. So this is what we are getting. So ODE45 takes more amount of time. And right now it is not visible because our system is really small and it is doing in fraction of seconds. But ODE45 is taking longer time compared to ODE23. Okay, now next problem. I hope this is clear to everyone. Now next problem. Temperature for an unsteady heat conduction of a sphere is function of time, space, both time and space or none. What is unsteady state? Unsteady state means variations are with both temperature, both time as well as space. So our correct answer should be this C, both time and space. We can write our equation as del T by del T. This is not for, I'm just writing a general equation, minus Ka del square T by del X square plus del square T by del Y square plus del square T by del Z square. Okay. So when it is steady state, this term won't be there. So it will be only space variation. But when it's steady state, it should be both space and time. Okay. Okay. So this was our 8th question. Let's move ahead. The ODE45 takes the function as, it takes the function as string argument. When we are dealing with our DIFF function, it takes as simple argument. So our answer is B, stiff argument. Now let's move ahead with question 10. Which of the following gives an indication of the ratio of conductive resistance to convective resistance? So what is my conductive resistance? Conductive resistance is given by L by Ka, and same, but in terms of convection, convective resistance is given by 1 divided by Ha. So ratio of conductive resistance to convective resistance, L by Ka divided by 1 by Ha, that is equal to H into L by K. So this is nothing but Biot number. So our correct answer is Biot number. But let's see about other numbers. So Nusselt number, what is Nusselt number? Nusselt number is convective heat transfer divided by conductive heat transfer. So convective heat transfer is HA delta T and conductive heat transfer is Ka delta T by L. So my answer is here H L by K of fluid. That is my this Nusselt number. Then Stanton number is given by convective heat transfer divided by mass flow rate into specific heat capacity. So that is nothing but Nusselt number divided by Reynolds number into Prandtl number. Those students who are preparing for your GATE examination, please well prepare this kind of question because they ask this significance of numbers. Okay, so our correct answer is Biot number. Okay, next question. Lumped parameter analysis for transient heat conduction is essentially valid for which value when Biot number is less than 0.1. So, okay, I will show you this small theory. before concluding our lecture. So I will open my notes only. I have written them. So see, lumped heat capacity analysis. What is there in this analysis? Consider a small metal casting of volume V, density rho, and specific heat C at temperature T naught, which is suddenly immersed in a large quantity of fluid at T is equal to T infinite. Since the thermal conductivity of metal is very high, it is reasonable to assume that there is no temperature gradient within the metal. So it is considered steady state within the metal, with means there is no gradient temperature in metal. The energy balance over a small interval dt. So when we solve this energy balance equation, that is minus mcp dt is equal to hat minus t infinite, we get this number t minus t infinity divided by t naught minus t infinity is equal to minus hat divided by rho v c. That is nothing but Biot number into Fourier number. Okay, Fourier number is alpha into T by L square. That is heat conduction rate divided by rate of thermal capacity stored in the solid. Okay, so this ratio Biot number, this is called Biot number. And when Biot number is less than 0.1, our error is maximum 5%. So anything less than plus or minus 5% is valid. So our answer is when Biot number is less than 0.1, this lumped heat capacity analysis is valid. Okay, now next question. What is the lumped heat capacity analysis? We just check what is lumped heat capacity analysis. Let's see the options. The analysis of a system in which it is assumed to be at no uniform temperature. No, this is not the case. So this is not the answer. So this is not okay. Next one. The analysis of a system in which it is assumed to be at spatially uniform temperature. This is the correct one. This is what is written. Since the thermal conductivity of metal is very high, it is reasonable to assume that there is no temperature gradient within the metal. So temperature of metal is remaining constant. So this means that spatially uniform temperature is there in metal. Okay. Now let's move with question number 13. Output of the following code will be, let's write it down here. Let's copy this. It won't run because we are going to see this part in detail for the next class. But for the sake of completing this question, it won't identify the variable y. So I need to write it here, I guess, y comma t. No, it is not. This syntax is not correct. Okay. So here we should, our answer is error. Okay. Our next question. A sphere, a cube, and a disk having same material and volume are heated to 900 Kelvin and left in air. So this is nothing but a problem of transient heat conduction. This lumped heat capacity analysis problem. These questions are also asked in GATE based on this lumped heat capacity analysis. So left in air, which of the following has the lowest cooling rate? So cooling rate will depend on this characteristic length, that is volume by area. For cube, volume is L cube divided by area 6L square. So it is L by 6. Disk, let's assume that it is cylindrical. So volume is pi r square h and area is 2 pi r h. Let's say r is equal to h is equal to L. So my this term is L cube divided by 2L square. So it is L by 2. And sphere, volume is 4 by 3 pi r cube. Let's say it is L cube and area is 4 pi r square L square. So it is L by 3. So this ratio is minimum for cube. So we can say that cube has the lowest cooling rate. Now next question. A beaker filled with hot water in a room cools from 70 to 65 in T1 minutes, 65 to 60 in T2 minutes, and 60 to 60 to 55 in T3 minutes. Then what is the actual case? So if we see this equation, T minus T infinity divided by T naught minus T infinity is equal to exponent of minus HE T divided by rho V Cp. So my T in first case is 65. Let's say ambient temperature is 25 divided by T naught is 65 minus, sorry, T naught initial temperature, that is 70, minus 25 is equal to proportional to exponent of minus T. Okay, so this number is 40 divided by 45 is equal to exponent of minus T. So T will be equal to ln of minus T will be equal to ln of. Okay, so this is one value. For the second value, it is 65 to 60. So 65 to 60. So my this value will be 60 minus 25 divided by 65 minus 25 equal to exponent of minus T. So here it is 35 divided by 40 T. So T2 will be equal to ln of 40 divided by 35. So here if we see this value turns out to be, I have written that 0.117 and this value turns out to be 0.13. So we say that this is the correct answer T1. So what we say that when we are cooling from 70 to 65, it will easily get cooled. But when it is going from 65 to 60, 60 to 55, it is going to take long amount of time. Okay. So our answer will be C. So this is all for today's lecture. So in today's lecture, what we check, we first uh, saw that heat transfer through cylinder. So for that we wrote heat balance equations and we solved those heat balance equations using lean solve command. After that, what we checked, we did numerical uh, ordinary differential equations numerical solution using Euler method. We first saw the theory how we can derive Euler methods equation. Then we checked RK2 methods and then we checked RK4 methods. Okay, and then we saw the actual solution and what we concluded that for the same value of h, RK4 methods give the accurate or answer closest to the actual system. But when we reduce the step size, Euler method is also giving accurate result. But what is the cost when we reduce the cost size? When we reduce the step size, our simulation time or our computational efficiency, we require more amount of time to solve the differential equation. So this is what we learned from today's class. After that, we took this small multiple choice questions when we learned this transient heat, this lumped heat capacity analysis part. Then we learned ODE23 and ODE45 solver. And we learned that ODE45 solver consumes more amount of time compared to ODE23 solver. Okay, so this is what is to for today's lecture. In next week's lecture, what we are going to see, we are going to see these two problems. First is series reactions, A is to B is to C, and the second problem that we are going to see is CSTRs in series. So two CSTRs, so two continuous stirred tank reactors are kept in series, and we are going to see how concentration is varying in this case. So this is all for today's lecture from my side. If anyone who is seeing these videos on YouTube, if anyone is having any query regarding to anything, please feel free to write me an email on using on this email ID. So that's all for today's lecture. So thank you everyone. We'll meet next week. Let me first stop the recording.